Okay, yeah, I want to give an overview of the PANDA experiment. And so as we already learned last week, so there were reports about different production mechanisms and reaction, which offer different possibilities. And we already learned that it's very useful to compare different production mechanisms in order to understand the particle's nature and gain information about the inner structure. So we heard about the photon production, which is a rather QED-mediated process, so a gluon-Pur reaction, but also about germanium decays. And I will talk about antiproton annihilation at PANDA, which is a rather gluon-rich environment. So the PANDA physics program is rather broad. So PANDA aims to study the hadron spectroscopy sector, which means PANDA aims to study light mesons, including exotic matter, also germania with the XYZ states, open charm, and also focus on baryon and hyperon spectroscopy. Nevertheless, also PANDA focused to study the nucleon structure with the different distribution. So, for example, generalized parton distribution functions, also the time-like proton form factor and transverse parton distribution functions, and also hypernuclei in another stage. So you see that the PANDA program is rather broad, and hopefully PANDA can contribute to various fields. So PANDA is currently under construction at the Facility for Antiproton and Ion Research in Darmstadt. So you see here how it's planned. So the blue part is already existing, and the red part will be built right now. And this is the current status of the construction site in February. So you see that the CIS 100 is almost completed, at least the underground work, and now the here basically the buildings are built and also the excavation is finished. So the PANDA experiment will be a fixed target experiment with an antiproton beam in the momentum range of 1.5 to 15 GeV, which means a maximum invariant mass of 5.5 GeV. And the design luminosity reaches from 10 to the 31 to 10 to the 32, which means that PANDA will be able to study physics cases with high event rates. Due to the design of the detector, PANDA will have an almost full coverage of the solid angle due to the forward spectrometer and the forward dipole magnet, and will have an excellent momentum resolution information, which we kind of heard also in the talk by Frank Nerling. So in antiproton-proton annihilations, there are basically two reaction types you can study if you are interested in resonances. So the first is the formation, which means that the resonance is directly produced out of the antiproton-proton system. So there you can reach all resonances with non-exotic quantum numbers, but you are not limited to the vector states as you are in E+ E- reactions, since you have antiproton-protons. And the resolution here is only limited to the beam resolution. So that means with this setup, PANDA will be able to measure very precisely these in the formation mode. On the other hand, there is the production mode, where you can study resonances with a recoil particle. That means you can also access resonances with non-exotic quantum numbers. And this means there is a high potential for new discoveries. So for example, a signal in production, but not information, would be very interesting. Another advantage with antiproton protons is that you have very high cross sections for gluon and light hybrid production, since this is a very gluon-rich environment, and also for charmed hybrids and molecules, which are similar to the ordinary hadrons. And also there will be high spin states accessible without any limitations, basically, on the quantum numbers. So now I will focus on the formation studies at PANDA. So as I said already, the resolution is only limited to the beam resolution and not by the detector. And if one, for example, compares antiproton-proton annihilation with different production mechanism, for example, initial state radiation or energy scan with electron-positron colliders, there one is often limited to the detector resolution or cannot reach higher beam resolutions. And with PANDA, there will be a beam resolution of 50 kV. So a very prominent example also from the past is the study of the width of the chi sub C1. So the chi sub C1 was measured as SPS 3, and there the width was determined of about 1 MeV with rather high uncertainties. And with, for example, the E835 experiment, which is quite long ago now, one was already able to get a better resolution here. And PANDA is expected to have 5 times higher beam resolution compared to E835. So there will be 2 different modes of the accelerator. One is the high luminosity mode, and there will be a high resolution mode. Yeah, for higher resolution, of course. So there was also a dedicated talk to this study of anti-proton-proton to X3872 to J-Psi-Rho, and we already heard a lot about this, but I just will briefly cover this again. So the X3875 is a rather 72 is a rather interesting state which sits right at the D star D threshold, decays to D star D and J-Psi-Rho, and we learned that both channels are very important to learn about the nature of this state. And here in this analysis, the main idea was to measure line shape with very high precision and to identify the nature by determining the Flatey energy EF by measuring the line shape. And here in this analysis, there were 20 energy points used around the nominal mass. And there were sensitivity studies performed if it's possible to distinguish the 2 scenarios of a bound or unbound state, basically. And the result was that it is possible to distinguish with more than 90% confidence for sizable Flatey energy. And so with the PANDA setup, this basically corresponds to about only a month of data taking. So here you see basically how the idea goes. So with the Flatey energy of less than 9 or so, you could say that it's a bound state if it's a smaller value, so a higher, so less negative value, it's a pure state. But you can see more on this by Frank Nalling's talk. So there is also another study ongoing, that is the mass-independent analysis of the process anti-proton-proton to 5-5. So this is an ongoing analysis, not yet published. And this offers a very gluon-rich environment. And the motivation behind is that there are lattice predictions that predict the tensor glue ball at around 2.4 GeV. And there was a former experiment, the JetSet experiment, which measured the cross-section and saw that it exceeds the expectations by 2 orders of magnitude. So this is very interesting, of course, and could be a hint for intermediate process involving, for example, some glue. And here now the idea was to study if it's possible to identify resonances in the 5-5 system by a model-independent partial wave analysis by describing the whole decay chain. So for this process, there were toy Monte Carlo data generated based on a 2-channel K-matrix scenario, including a hypothetical tensor state. And here the magnitude and phase motion of the 2++ wave were extracted using 36 data points between 2.25 GeV to 2.6 GeV with 10,000 events at each point. And here you see that it's very powerful in extracting the generated contributions. So this is already a very nice result that one can also do such rather spectroscopy-like studies. So now I will turn to production studies and partial wave analysis at PANDA. So the production channels are usually more complicated due to the contributing intermediate processes. So with the recoil particle, you have much more combinatorics to take into account, and therefore often partial wave analysis are needed and help to identify intermediate resonances and study their properties. So first of all, on the production side, the challenges are that there are many contributing initial proton-antiproton states, as you see here on the right side in the upper plot, already with a beam momentum of around 3 GeV, you have a significant contribution of angular momenta of 5 or more. And therefore, sophisticated tools are needed and to be applied to, first of all, investigate this production process, but also to describe the overlapping resonances in the various decay channels. So for this purpose, there have been analysis going on using data from the crystal barrel Lear experiment. And they are an excellent opportunity, of course, to investigate the physics aspects, which are also relevant for PANDA. So this is real data, and basically you can't have any better data to describe the reality as real data. So therefore, this is very useful. Just as a reminder, the crystal barrel experiment was an experiment which operated between 1989 to 1996. It was a fixed target experiment at Lear. And it was designed, as you see here in this, in the lower plot, it's a symmetrical detector. So this was a detector designed for antiproton-proton annihilation at rest. And it's very famous because there the observation of the light scalars, later named the global candidates, was carried out. And here a beam momentum range of up to 1.94 GeV/c was reached. So there is an overlap with PANDA, which is very nice to have to, see if one can reach the same or better performance with PANDA, of course. So, but PANDA will have a 100 times higher luminosity. That means the data that was taken with crystal barrel in a year will be available in only 3.5 days. So now in the following, I will discuss 2 of those analyses. First of all, the investigation of the antiproton initial states in the reaction to omega pi 0, and I will also present a coupled channel analysis of antiproton-proton to pi eta, and kk pi. So first of all, the study of antiproton-proton to omega pi 0. There were several crystal barrel data sets used for this analysis at different antiproton beam momenta, from 600 to almost 2 GeV. And here the omega was reconstructed in its 2 main decay modes into 3 pions and gamma pi 0. And the contributing L max, so the maximum angular momentum, was investigated. And you see for both decay modes that it was possible to identify the maximum contributing angular momentum. And you see also that the data for the 3 pion decay, which is the dominant decay of the omega, is here a bit sparse compared to gamma pi 0. And this is because the crystal barrel detector did not have a good coverage for charged particles. So therefore, of course, the PANDA detector will be much more performant in this study. So furthermore, it was possible to extract the spin density matrix of the omega. So the spin density matrix basically contains all information of the production mechanism. And here you see the different matrix elements. And you see in this row 0, 0 that first of all, one observes spin alignment. So there is something more complex ongoing on the in the production process. And there can be probably also resonances involved, might hinting that there is a more complex structure here in this row 0, 0. So this is very interesting to see, and would be probably very interesting to perform again with PANDA. So now I will talk about the coupled channel analysis. This was already covered slightly by Bertram last week. And the idea here was to study these 3 decay channels using crystal barrel data at 900 MeV and combining it with pi scattering data for the isospin 0 and isospin 1 waves and describing all this data simultaneously. So there were many A0, A2, F2, and F0 resonances contributing. So this was a very complex fit. And this was all described using a K-matrix formalism in the p-vector approach. And the advantage here is also Bertram explained in more detail was that one gets constraints due to common production amplitudes and pole parameters. So one can share most of the parameters between the channels. And the very interesting thing was here that it was necessary to take into account a exotic pi1 wave, which contributes significantly in the pi eta system. And here in this table, in the last entry, you see that these waves contribute with almost 17%. So that also shows in reality that the hybrid production is similar to light meson production in antiproton-proton annihilation as one expected. And furthermore, it was very interesting because here on the right side, you see the phase motion so the phase difference between the pi1 and A0 waves, which was also before carried out by compass. And this is not a fit here, but it's just a comparison. So it's very interesting that with the P/P analysis, one basically gets the same shape without using this data. So with a complete different production mechanism. Here you see different contributions that were extracted, and also something that can PANDA do better for sure is in the lower row, in the KK angle. There is a very bad efficiency because again, crystal barrel was not so good in detecting charged particles, and here PANDA, for example, can improve. Here you see the scattering data that was also described simultaneously, fits very nicely. Yeah, so another analysis I want to present, which now goes to the baryon sector, is the study of excited baryons in the system cascade plus bar lambda k minus final state. And the motivation is to do this feasibility study, since PANDA also aims to study baryons, since the production cross sections are expected to be high. So in this table here on the right, you see that there are rates of several baryons per second are expected for various channels to be studied. And the main motivation is that, as you know, the knowledge in the strange baryon sector is very sparse. So there are many states predicted, but not many have been found yet. And with PANDA, it will be possible to study charged and neutral decay modes. And this will be very interesting for the search of new strange baryons. So here a feasibility study was performed, and the main idea was to determine spin parity quantum numbers for specific cascade resonances. So there were 2 cascade resonances simulated, including this detector response, and the model included interference effects and the proper angular distribution and barrier factors. And as you can see here in the tables on the right, there's always shown the generated quantum numbers and the assumed quantum numbers in the fit. And you can always see that in the diagonal, this is the best fit. So that means that the fit was able to reproduce or to find the right quantum numbers. And this is very interesting to see. Although, of course, these models are rather limited and might not present the real nature, but therefore we, of course, need to measure. Yeah, this was the decay chain. So, but PANDA can also contribute on another level. We have heard also about form factors, and so PANDA is aiming for the electromagnetic form factors of the proton. So as you know, there's the electric and the magnetic proton form factor, and there are analytic functions of Q squared. And at low Q squared, this is interesting to probe the size of the nucleus, and at highest Q squared, probably the theoreticians are interested in testing the QCD scaling. So these are very fundamental quantities, but they are not yet well measured. So there is very little data, and often only the ratio R between those electric and magnetic form factors is measured. So there were feasibility studies performed of the decay chains p bar to electron positron and mu plus mu minus. And these studies suggest that PANDA will be able to, first of all, measure the muon final state for the first time, and to improve measurements with higher statistics and also access the relative phase between the electric and magnetic form factor. And here you see in this plot, these purple and bluish markers are that the data PANDA can contribute. And you see also that there will be measurements at very high Q squared, which were not able before probably. And this is the results for the muonic final state. And also there, PANDA can contribute with rather small errors. So yeah, as a summary, I probably have shown you that antiprotons are unique and decisive probes to tackle open questions in hadron spectroscopy. And hopefully PANDA will play an important role in the regime of spectroscopy. And due to the gluon-rich environment, we expect high event rates. In the formation, PANDA will be able to measure precisely the different widths with line shape scans, for example, of the X3872. And this is already day one physics. And in the production scenario, PANDA, or basically we already showed that using sophisticated partial wave analysis tools, one is able to study exotic quantum numbers. And we already have these tools available. And we already gained valuable experiences from the crystal barrel experiment. And this is beyond the proof of concept. So as you saw with 30 years old data, we were able to find a new exotic wave in this data. So this is beyond showing that it's possible. And so there is a very high discovery potential. And yeah, already very promising studies were performed. And this is only a snippet of the possibilities PANDA will probably have in the future. And as you might know, so all over the world, there is a lack of antiproton beams. So therefore, PANDA will have a unique position and great capabilities, which were already shown in the past, for example, by Crystal Barrel. And yeah, more feasibility studies are ongoing and upcoming now. So stay tuned for that. And yeah, thanks and stay healthy.
Thank you, Meike, for the nice talk and the nice overview. Actually, you concluded your talk even 2 minutes before the time. You had 25 plus 5, but then we have a bit more time for questions. So I see one hand raised. Christophe, please go ahead.
Hi, Meike. Thanks for the nice talk. Can you go to page 18, please? You didn't really comment on it, but maybe you're not the right person to answer because it's, as you might have guessed, some sort of theory question. But you write there for the unphysical region, you want to look at pp bar to e plus e minus pi naught. So are there studies that show that the role of nuclear excitations in the intermediate state can be controlled?
Well, there are not any feasibility studies on that yet. So as far as I know, I think this is something that might be done in the future. But as you say, for example, excitations due to this pi zero are probably hard, but I don't actually know if there were any studies yet, and for sure not at PANDA yet.
Okay, thank you.
I see also Biplap wants to ask a question. Biplap?
Yes, thanks for this very nice talk. It's just to quick question. So when, what is the status of the experiment? When do you plan to start data taking? Probably I missed that. If you already mentioned it.
No, I did not mention, and I think there was also some similar question last week. So the official timescale is 2025. So as you know, there is currently the construction of the SIS-100 storage ring, and the rest will follow, hopefully. But you know, the situation is very much challenging now due to the things that happen worldwide. So of course there will be some delay, but I think no one can really give a valid date when this will actually happen. So the official date is 2025, but let's see how the things change and go.
Okay, thanks.
I thought it was more likely 2030, and I was wondering if people can really start by 2030, because it's already 2022, and you already mentioned that there are now problems also in Europe, and there are contracts with the Russians, and I don't know how the situation will handle in the end. Okay, there are further questions? I don't see anyone, so we thank Meike.